This is an introduction to Chapter 14, where we are looking at our first conservation law, which is for work and energy. And in Chapter 15, we will look at the impulse momentum conservation law. In Section 14.1, we start off with the definition of work. Now, we saw work in Physics 161, and although we are using many of the same equations in this chapter that we had in Physics 161, you may not recognize them at first glance because in Physics 161 we used a W for work, so that would be the U that we have here, or the U that we have here. For work, that would have been a W in Physics 161. And for kinetic energy, we have in dynamics a capital T, whereas in Physics 161 we probably used KE for kinetic energy. The good news is that the notation that we are using now in dynamics is standard notation, so you will hopefully see it again in your other courses and it won't change anymore after this. Okay, so we will start off looking at the definition of work. So they say here that a force F will do work on a particle only when the particle undergoes a displacement in the direction of the force. So if you have a force pointing this way, but the displacement vector is this way, then there is no work done. So that's why we have the cosine of theta here, and theta is the angle between the displacement vector and the force vector, but you may recognize that. We could write that as the dot product. So if you look at equation 14.1, we have the work is the integral of f dotted with dr, or you can say the integral of f cosine theta ds, where theta is the angle between the force vector and the displacement vector, and I think they say it here, the magnitude of dr is ds, which is something you want to keep in mind. Usually, like back in Physics 261, the magnitude of the vector ds was just ds, but here the magnitude of dr is ds. And then I guess if I want to make this the work, I'd have to integrate that. Okay, so in equation 14.1 we have the definition of the work. It's the integral of either the dot product or f cosine theta ds. So you can use either definition there. Okay, now if the force is variable, then you have to know how the force depends on the position and how the angle between the force and the displacement vector depends on the position. So they say you can integrate this provided the force and theta can be expressed as a function of position, since you're integrating here with respect to ds. Now, a nicer case would be when the force is constant. So if the force is constant and the angle theta is constant, which would be the case if the particle is moving in a straight line and the angle of the force isn't changing, then you can pull the force outside the integral and you can pull cosine theta outside the integral, and then you'd simply get the constant force times cosine the angle times s2 minus s1, which is the displacement. Then they talk about the work done by the weight or the force of gravity, and we're going to come back to this in a minute. They also talk about the work done by a spring force. Now, both of these forces are conservative forces, and that means we have a potential energy associated with those forces. So that would be the gravitational potential energy and the elastic potential energy. In order to determine whether a force is a conservative force, if you calculate the work done and your starting point is the same as your ending point, so you can go all the way around, it doesn't really matter where you go, as long as you end up at the same place you started from. If you calculate the work and you get 0 when the starting and ending point are the same, if you always get 0 when the starting and ending point are the same, then that force is a conservative force. So for the force of gravity, if you lift something up in the air and then lower it back down again, and you calculate the work when you go from here to here and then back down where you started from, you get 0 because you're starting and ending at the same place. Similarly, for the spring force, as long as you're starting and ending at the same place, the work done is 0. So there are potential energies associated with those forces. So instead of always finding the work that's done by a conservative force, you could use the potential energy instead. And we're going to see how that works in, I think, section 14.6. So in the example problems that they have earlier in the chapter, they're going to stick with equation 14.7. However, I would rather not treat the problems in equation 14.6, in section 14.6 completely different than how we treat the problems earlier in the section. So I'm going to try and treat all the problems the same, but if you look in the textbook, you may notice that they do things a little differently. And it doesn't really matter which method you use to solve the problem, whether you use the work done by the force of the spring and the work done by the force of gravity or the potential energy, and it's good to know how to do it both ways. But I would prefer to use the potential energy just so that we have one way that we can approach any problem and it always works. Okay, now in section 14.2, we come to the principle of work and energy, which you may remember from Physics 161, and I think it would be worthwhile just to rewrite this equation as you saw it in Physics 161 so it doesn't look so strange to you. So this is the sum of all of the work done on the object. So this I'm going to call the total work, and I'm going to write it how we would have seen it in Physics 161. Okay, so in Physics 161, we have the total work, and then if you bring T1 over to the other side, that would be the change in kinetic energy. Okay, and then in our course, we have the total work, and I just want to take a look at how we have this on the equation sheet. So this is equation 14.7, which is the same as what we have here. So this is the sum of all of the work, so that is the total work, and that's equal to the change in kinetic energy, which would be T2 minus T1. Okay? Now, this is getting a little bit ahead of where we are in the textbook now, but let's go and look at section 14.6. Maybe it's section 14.5. No. Well, they talk about the conservative forces and potential energy in section 14.5 and show you how you get the potential energy. But then in section 14.6, they have, equation 1420, which is what I'm looking for. Okay, this equation is similar to equation 14.7. I want to write that out again, actually. So for 14.7, putting the T1 back on the left-hand side, we have T1 plus the work done by all of the forces is equal to T2. Okay, or in Physics 161, that would be KE1 plus work total is equal to KE2. Okay, and then we have equation 1420, which says T1, which is the initial kinetic energy, plus V1, which is the initial potential energy, plus the work done by non-conservative forces is equal to T2 plus V2. Now, in the textbook, you wouldn't see them solving problems with equation 1420 until you get to section 14.6, but I would like to use this equation earlier just so we have a consistent approach when we solve the problems in this section. Okay, and in Physics 161, this would be initial kinetic energy plus, now here's what you have to keep in mind. In a given problem, you may only have one type of potential energy. It could be gravitational potential energy, it could be elastic potential energy. Sometimes you have gravitational potential energy and elastic potential energy. So here, for equation 1415, we see that the potential energy, which is what we have here, could be gravitational potential energy plus elastic potential energy. So this would be gravitational potential energy, and I don't know, I think in Physics 161 we probably just wrote out the elastic potential energy like this, but let's just say EE for elastic potential energy. So kinetic energy plus gravitational potential energy plus elastic potential energy, that's the T1 plus the V1, plus in Physics 161 this would have been work other, so work done by forces other than the gravitational force and the force of the spring is equal to final kinetic energy plus final gravitational potential energy plus final elastic potential energy. Okay? Now, it gets even better because not only are we writing the equations in dynamics different than how we wrote them in Physics 161, but even in Physics 161 we had different ways of writing this equation. So what you might find more useful is to actually take the definition of kinetic energy and put it into this equation here, and take the definition of work and put it into the equation that we have here. So that's what I have here written out on my equation sheet. And you might want to write this out on your equation sheet as well. And this is where I usually start when I solve problems in this chapter. So rather than having to first pick whether I use equation 1420 or 14.7, and then after I do that, look back at the definition of kinetic energy, which honestly, like, it shouldn't be too hard to remember that the kinetic energy is 1/2 mv squared. But we would have to take that and use it in the equation here. We'd have to take the definition for gravitational potential energy and put it in here, and elastic potential energy and put it in here. And then if you did decide to use equation 14.7 instead of equation 1420, then when you calculate this work, you'd use this definition here, but when you put it in the net force, that might include the force of gravity and the elastic force. And so that would be a little more work if you're going to use equation 14.7. So if you're using equation 1420, you don't have to worry about finding the work for the gravitational force and the spring force because we are taking care of that with the potential energies. Okay, so we have the kinetic energy, which is 1/2 mv squared. For the potential, that's gravitational plus elastic. Gravitational is W, which is the weight, times Y, which they do that in the book, which is why we have Y here. But if you're talking about the weight, if you're going from here to here and the potential is changing, you must be changing elevation. And so Y would be in the vertical direction. So what I think is nicer, rather than using Y, because you might, decide to use a coordinate system in a problem where Y is in the horizontal direction instead of the vertical direction. So if you say mgh for the gravitational potential energy, h is a height, and then that works nicely. I like to use that for the gravitational potential energy because it just kind of takes care of itself there. And a height could be positive or it could be negative. For the gravitational potential energy, you have to choose a reference point where the height is equal to 0, and then if you're below that height, you have a negative gravitational potential energy If you're above that height, you have a positive gravitational potential energy. So if your reference point where h is equal to 0 is different than my reference point, you would have a different gravitational potential energy than I have, but we would agree on the change in gravitational potential energy, which is really the only thing that matters. And then we have the elastic potential energy, which is 1/2 times k times s squared. And again, remember that they're using s for the force of the spring, and that's the same s that we have here. So that's for the spring, but you might have another s in the problem, which isn't necessarily the same as the s that you have in the equation for the elastic potential energy. So just keep that in mind. And then we have the work done by non-conservative forces. So this is the definition of the work, and this would be the sum of the forces other than the gravitational force and the elastic force, which usually is probably only going to be one other force. And then we have final kinetic energy and final gravitational potential energy and final elastic potential energy. Okay, so that's what we get from actually putting the definitions into equation 1420. And we'll see how to use this equation when we get to some example problems. So this very useful equation is combining 14.1. Instead of 14.7, we're using 14.20. The equation for kinetic energy, 14.15, 14.13, and 14.14, you would take these two, put them in here to get the total gravitational potential energy, and then put that in there. So if you just use this equation instead, that kind of takes care of 2 rows of equations on the equation sheet. The middle row here is for section 14.4, where we look at power and efficiency. So there are other equations for that, which we'll see when we get there. Okay, so I think we are going to go back now to where we left off. Okay, so we had work done by the spring force and work done by the force of gravity. And I don't actually think we said yet how they are related to the potential energy. You could figure that out from looking at the equations here, but I think if we go to section 14.5, you can see okay, so they define the elastic potential energy here. They define the gravitational potential energy here. If we calculate the work done for the force of gravity, which they do here, so this is negative W times delta Y. Let's write this out so we can keep track of everything. Okay, so this is work done by, I'll call it Fg for the force of gravity, is negative, and instead of the weight, I like to use mg times delta y. Okay, and then before we go back to section 14.5, for the force of the spring, so work done by the force of the spring is minus 1/2 ks2 squared minus 1/2 times ks1 squared. Okay, so now we can go back to section 14.5 and there we go. If the gravitational potential energy is W times Y, we call it little g, so we'll do that, mg times y, then this is equal to minus mg. Delta y is y2 minus y1, so that's minus mg y2 plus mg y1, and mgy2 would be gravitational potential energy at 2, and then that would be plus Vg1. But we could pull out the negative sign and say, well, Vg2 minus the gravitational potential energy at 1. So that's the change in gravitational potential energy. So negative delta V. So the work done by the force of gravity is equal to the negative change in gravitational potential energy. And if you look at equation 14.7 and equation 14.20, you would just need to say this: the total work is equal to the work done by non-conservative forces plus the work done by, well, I called it the force of gravity here, but I guess you could just put in the little g like we have there, plus the work done by the force of the spring. And then to get to equation 14.20, you could, if you put this in for the work done by the force of gravity, and then we're going to see what you would have to put in for the work done by the elastic force, then you would get equation 14.20 from equation 14.7. Okay, so now the elastic potential energy is 1/2 ks squared. Elastic potential energy is 1/2 ks squared, so this becomes negative 1/2 ks2 squared would be the final elastic potential energy minus the initial elastic potential energy, so that is the change in elastic potential energy. Okay, so let's actually do this and see. We would get is equal to the sum of the work done by non-conservative forces minus, this would be the change, we'll go back to what we have here, and then plus the work done by the force of the spring, which would be the change in elastic potential energy. So this would go in for what we have here, and we would have the initial potential would be positive because we have two negative signs. The final would be negative, but then you bring it over to the other side of the equation and it's positive. So hopefully you see now how equation 14.7 and 14.20 and this equation that we have here are all related to each other. So again, we'll go back to the beginning of the section, or the beginning of the chapter, wherever it was we left off. Okay, so that was 14.1. Okay, so now for 14.2, we have work and energy, or we talked about equation 14.7 already. Pay particular attention when you have a green box and read through it carefully. And that brings us to section 14.3. And this work of friction caused by sliding, that's very interesting and you should read through it on your own. So we said that the force of gravity and the elastic force, or the force of the spring, are both conservative forces. So if you take any path but end and start at the same point, then the work done by the force is 0 if the force is conservative. Friction is not a conservative force because if you take something and you slide it this way and then slide it this way and come back to where you started, the work done by the force of friction in that case is not 0. So remember we talked about the angle between the force and the displacement. So if you're sliding something this way, your displacement's pointing in this direction. Friction is going to oppose the motion, and so the force of friction is going to be pointing in the opposite direction. But now when you slide the object back this way, your displacement is this way, Now your force of friction is still opposing the motion, so friction is going to be pointing in the opposite direction. So friction is not a conservative force, so there's no potential energy associated with friction. And I should point out here that when you use this equation, here in equation 1420, they say the work done by non-conservative forces, but unless you know what the associated potential energy is for that non-conservative force, well, if you don't know what the associated potential energy is, you can't really write that in your equation here as potential energy. So I kind of like this better where we say forces other than the force of gravity and the force of the spring, because it's not necessarily saying that these forces are non-conservative. It's just saying that we didn't include the potential energy for that force, so we have to find the work done by that force. Okay, so you could have other forces which are conservative, but unless you're actually putting the potential energy for that force into the equation, then just include it when you find the work done by forces other than whatever you have the potential energy for. Okay, so what happens here, and they talk about with the frictional force, is that when you slide an object on a surface, you can't actually, or you shouldn't treat the surface as a rigid surface. So the little teeth that you have here on the surface are actually deforming. And because they deform, the actual value for the displacement that you would use is less than the displacement that the object actually had. So because the teeth are going to slide with the object for a little bit and deform as the object goes over it. So the distance that you should use for calculating that work is s prime, which is less than s. However, we also know that when you rub things together, you generate heat. So read through this on your own, but what we take away from this is that the total work done by the force of friction, which naively we would calculate as the force, which is the force of kinetic friction because the block's actually moving, so that would be coefficient of kinetic friction times normal force, times the displacement s, which is how far the block actually moved. That is equal to the external work. So this is using the s prime, which they're saying is what we really should have used. So now you're missing something because s is greater than s prime. And what you're missing is actually the internal work, which is what is causing the temperature to rise. So that's interesting, and I encourage you to read that page over on your own. And that brings us to the end of the reading material for section 14.3. So now we're going to start to look at some example problems from section 14.3, but we are going to use some of the equations that we looked at from sections 14.5 and 14.6 when we solve the equations in section 14.3. At least I'm going to do it that way. If you look at the example problems in the book, that's not how they do it, and you don't have to do it that way if you'd rather use equation 14.7 and find the work done by all of the forces. You can do it that way, but I think it's a lot easier to use the potential energies, and it allows us to approach the problems more consistently rather than trying to determine if you're doing the homework problems, you know what section of the book they come from, but if you always approach problems with work and energy using this equation here, then you don't have to think about whether it be a problem from section 14.3 or a problem from section 14.6. All right, so that's all for now, and in the next video we will start looking at some example problems.